Good morning, students. Mr. Carver here. Got two warm-up problems. Try them. Pause it, work them. When you're ready, hit play. I'm going to work them now. All right, so number one, we're looking at the shape with focus points at 3, 2, and 3, -4. I've got those labeled. Vertex at 3, 1. Just by looking at the focus points and the vertex, we can see, hopefully, this is going to be a hyperbola. Opening up or down, up and down, excuse me. So using symmetry, I know that my other vertex is right here at 3, -3, which then puts the center right here. Whoops. There we go. Puts the center right there. All right, so just by knowing those 5 attributes right there, I can at least come up with the beginning, or the beginning of the equation. So here's what I've got so far. I've got partial credit. All right, cool. Now, it looks like the center is going to be at 3, -1. It does open up and down, so that means I've got to have my y first. So I want it to go down 1. That's going to be y plus 1, partial credit. Then it's going to be then shifted to the right 3. That's x minus 3, and again, partial credit. Now, distance, rather, along my transverse axis. That is the axis that goes from vertex to vertex. From center to vertex is 2 units. That means up and down 2 units from the center. Makes the denominator underneath the y term going to be the square of 2, which is going to be 4. Then I've got the focus points, which are going to be 3 units out. Now, that is not the denominator underneath the x. So I'm going to make, just for the time being, I'm going to make that b squared. I know that in order to find the distance between the center, or rather the distance from the center to the focus point, what I do is I take the 2 denominators and I add them together. So I'm going to do this down here. This is going to be 4 plus b squared, and I will get then the square of the distance from the center to the focus point. That's going to be 9. So my b squared in this case is going to be equal to 5. That is that denominator right there, and that equation is the equation of that hyperbola with those attributes. All right, number 2. So I've got a parabola opening to the left. I've got a focus at -3, -2. If I know that the parabola opens to the left, that means I have to have a vertical LR, and it is 6 units in length. Remember that the LR passes through the focus point, and it's a chord, rather. The endpoints of the chord actually fall on the sides of the vertex. Excuse me. They actually fall on the parabola, which means that my vertex is going to be somewhere to the right of the focus point if it's opening to the left. Now, how far is the question? Well, one thing that we can start with is we know that the length of the LR is equal to the absolute value of 1 over A, and I know in this case that that is 6 units. If I go ahead and solve this, I get A is equal to 1/6. So I know at least part of my formula. In fact, up here I can start this. I've got x is equal to -1/6. It's negative because it has to open to the left. Now, I just need the ordered pair of the vertex to get this completed. Remember that the distance from the focus to the directrix, the distance from the focus to the vertex is 1 over 4a. So in order to find that distance, I'm going to take this a value right here and plug it into that formula. 1 over 4a is 1 over 4 times 1/6. That is going to be 3/2 when I copy dot flop it. So it's 3/2 to the right of the focus point. So it's 1.5 units. There is my vertex, which is going to be at -1.5, -2. So I want it to move down 2. That means this is going to be y plus 2 in here. That's going to be squared. And then I need to move it to the left 1.5. So that's going to be minus 3/2. And this, my friends, is the equation of the parabola with those attributes. All right, people, so you've had 2 days of calculus vacation. So now it is 9/3, and we are going to be doing calculus to parametric equations. Nothing you guys can't handle. All right, let's get started. All right, now there are going to be times when you've got parametric equations where going through the 3 steps that I gave you in section 9.2 just they're just not practical. In fact, it's impossible to eliminate the parameter and combine them into a single rectangular function. So there's other ways to determine slope of a parametric equation without having to go through and eliminate the parameter and actually graph it. Let me give you an example of what I mean right now. So one of the ways that you could go about this is to actually eliminate the parameter, combine them in such a way that the t is now gone and you just are relating x to y, but it is super impractical, if not impossible in this case, because you've got a very complex, non-solvable or not easily solved for t, this x function right here is kind of the problem. So there's other ways around it. If I'm looking for the slope of this eventual curve without actually graphing it, what I can do is use the fact that slope is given by dy over dx. Change in y over change in x. The thing we need to keep in mind, though, is that y is a function of t and x is a function of t. So what we're really looking for is change in y with respect to t over the change in x with respect to t. And if you think about these as being two fractions, when you copy dot flop this, you actually do get back to the original expression of dy over dx. It's just that now they are both in terms of t. So in this case, let's say that I was looking for the slope of the parametric equation at t is equal to 3. Easy peasy, lemon squeezy. All I do is derive the y, put it over the derivative of the x, and I plug in 3 for t. So here we go. My dy over dx in this case is going to be equal to simply just the derivative of y with respect to t, which is 3t squared plus 0, over the derivative of my x equation with respect to t. That is going to be 2t plus 3. And then from here on out, all I have now is a slope machine in terms of t. All I have to do is feed it my t, and it will give me rectangular slope. And rectangular slope is dy over dx. So I plug in 3 in the top, I get 27 on the top. Plug in 3 in the bottom, that's going to be 9. The slope is 3, so it's up 3 over 1. That is normal slope, rectangular slope, rise over run. This is your answer. All right, now we can go through a similar process to determine concavity. Remember, the first derivative is a slope machine, the second derivative is a concavity machine. So I think it stands to reason that if you are unable to eliminate the parameter and come up with an expression rather for slope in rectangular form, it's equally difficult, if not impossible, to then find the second derivative in rectangular form. We're going to keep it in parametric form. That is, we're going to work with the x and the y in terms of t. So let me just show you where this equation for the second derivative comes from. And again, this is what we're looking for. And the notation of the second derivative, again, is a little odd. If you recall from first semester, the expression rather for the second derivative is d squared y over dx squared. And if you recall, the reason is because d over dx is a command to derive the derivative, which gives you then 2d's, which is where this squared comes from, and I get 2dx's, which is where this comes from. All right. Technically, the denominator should have parentheses, but who's counting? All right, here we go. Let's get rid of this. Get rid of this. The second derivative, again, is equal to the derivative with respect to x of dy over dx, which is algebraically equivalent to the derivative with respect to x of dy. Actually, that's incorrect. Let me get rid of this. Sorry, guys. So the derivative with respect of dy dx really is equal to the derivative with respect to t, not x, with respect to t, because these are both expressed in terms of t, of dy over dx. Now what I need to do is I need to make sure that this chain, or this product here, this product right here, matches this product right here. And as it stands right now, it does not. don't have any dt in this formula right here, and I need 2 dx's in the bottom. So in order to make that happen, I'm going to multiply that expression by dt over dx. So what I have here is this dx, this dt dx, rather, this orange underlined section right here. What I want to do is then move it to the denominator, and I've got to flip it, of course, when I move it to the bottom, which gives me then this. This is the derivative with respect to t of dy dx all over dx over dt. So let's go ahead and work through this and find the second derivative of this parametric equation right here. I already know from the previous section that my first derivative, the expression for my first derivative, dy over dx is equal to 3t squared all over 2t plus 3. That's the expression in terms of t for my slope machine. If I'm then looking for the second derivative, d squared y over dx squared, I just follow the formula in this red box here. So here's what I do. I take the top and I derive it. I'm going to use the quotient rule. So again, remember, it's been a long time since we've done the quotient rule. I have low d high minus high d low all over the square of the below, the square of the denominator. That's this portion right here. Now what I want to do is I want to put that over the derivative of x with respect to t. The derivative of x with respect to t is 2t plus 3. Again, I'll just put that over 1 so you can kind of see what's happening here. This is your big main fraction bar right here. So what I want to do is clean up the top and copy dot flop with the bottom fraction. So this is going to give me, this is d squared y over dx squared again, second derivative. This top then simplifies to, what is that, 12t squared plus 18t minus 6t squared. So what my second derivative numerator is going to be, that looks like 60 squared plus 18t. I actually have Verizon, but that's all right. And this is going to be over then 2t plus 3, the quantity cubed. Now, if I'm looking for concavity at t equals 3, sorry guys, technical difficulty. All right, so if I'm looking for the concavity at t is equal to 3, remember the number of the concavity doesn't matter, it just matters whether it's positive or negative. You can see when I plug it into the top, it is a positive, plug it into the bottom, also a positive, so the graph is concave up at t equals 3. If I ask you for a rectangular point, what you would do is take your 3 and plug it into the x and y, which generates then an ordered pair. Okay, so that's the second derivative. Let's continue. Okay, so two more things that we're going to find when it comes to parametric equations. It is going to be arc length and surface area. Arc length being the length of the curve. The reason it's a calculus problem is because it actually is curvy. I'm just going to give you those two formulas. At the end of this video, if you're interested in seeing where it comes from, you can just watch this through to the end. If you're not interested in seeing where it comes from, I will completely understand. All right, so here are the formulas. All right, there is your arc length formula. This is going to go from A to B. A is a lower t-bound, B is an upper t-bound, and then the innards of this square root is going to be the derivative of the x function squared, and then the g prime of t will be the derivative of the y function squared. I should probably mention that as well. In this case, x is equal to f of t. It is a function of t. Y is equal to g of t, also a function of t. All right. Now, the upside about this is that you will be using your graphing calculator. In Chapter 9, you will not have to integrate and evaluate these by hand. All right, so let's work an example. let's say I ask you to find the arc length over the parametric curve. X is equal to t squared plus 1. Y is equal to 4t cubed plus 3 over the t interval negative 1 to 0. All you have to do is follow this formula right here, and you got it. I'm now going to integrate from my low t to high t, that is negative 1 to 0. And then I'm just going to plug in to my square root the derivative of the x value, that is 2t, and then I square that. I'm going to add that then to the derivative of the y, which is 12t squared, square both of those derivatives, and that is dt. Now, the nice thing about this is you're using your graphing calculator. The graphing calculator doesn't care whether you are putting in t's, x's, y's, w's. You're going to plug this into your graphing calculator just as is. You can actually simplify the innards if you like. You don't even need to. You can write it just like that. That'll go into y1. Then you're going to graph that, and you'll use your commands. It's going to be second. So what you're going to do is graph this into y1, as I said before. Then you're going to do second trace. It's option number 7. Then you're going to put in your lower bound, enter, your upper bound, enter. It'll shade it and then give you the actual numeric value of your arc length. And in this case, it's going to be 4.149 units. All right, easy as that. We're also going to do then, take that arc length and revolve it around an axis of revolution, just like we did back in Chapter 6. And there is a different formula for that, so let's do that right now. All right, surface area for parametric equations. It's very similar to surface area in rectangular form. If you recall, what we did was we took the equation for arc length and we multiplied it by 2 pi r, because 2 pi r is the formula for the circumference. So the way we looked at it was, back in the day when we did rectangular form, we had something like this. What we did was we took a little bitty tiny piece of arc length, and then we took that and revolved it around the axis of revolution, created this like paper, very thin paper ring. Because surface area is nothing more than the accumulation of the areas of all of those individual paper rings all put together. So it was the tiny little bit of arc length times the circumference, and the distance around, of course, is 2 pi r. The same thing can be said in parametric form. So I think this should make sense. Here are the equations for surface area in parametric form. All right, so the 2 pi is a constant and can actually be taken out to the front. But I would leave it in since you're going to be using your graphing calculator. So you've got your 2 pi r here, that's the circumference, and then all of this is the expression for arc length, the tiny little piece of arc length that you're adding together through the magic of integration. Now, just like it was back in Chapter 6 for disk, shell, and washer, the difficult part is getting this expression for r here. And I'm going to work through a couple of those so that you can see it. So here's, let's use the same formulas that we did before. Let's take x and make that t squared plus 1, just like we had before, and then y is equal to 4t cubed plus 3. And let's say I want to take that, that parametric curve, whatever that looks like, and I want to revolve that around the x-axis, kind of like we have in this picture right here. And again, I am going over this interval from -1 to 0. Again, those are t intervals. So what I've got then, I've got the integral from -1 to 0. I've got 2 pi times my r. Now, if you think back to Chapter 6, the r measurement goes from the x-axis up. Remember, that is just nothing more than y. But again, this is all with respect to t, so I can't plug in y. I've got to put in 4t cubed plus 3, and then I go about the same arc length expression inside the radical. This is going to be the derivative of the x, that is that is 2t, the quantity squared, plus then the derivative of the y, which is 12t squared dt. Now you're going to be using your graphing calculator on this, so all of this goes into y1. It is second calculate number 7 from -1 to 0. Of course, you won't be entering t's, you'll be entering x's using the variable button on your graphing calculator, just like you did every curve since about 6th grade. Okay. Again, it'll draw it and shade it and give you the numeric value for it. All right, now let's change it up just slightly. Let's say that I went around the y-axis. In fact, let me do this in orange. I'm going to go around the y-axis. Everything's going to be the same except for that expression right there. And remember, arc length and surface area, doesn't matter what variable you work it in, you just need to pay attention to make sure you get the right function in there. So this now will be the integral from -1 to 0. I've got 2 pi, but now my r goes from the y-axis out to the curve right here, and if you remember that from chapter 6, y-axis over is nothing more than just x, but again, I'm integrating with respect to t, so that's t squared plus 1, and then all of this, of course, goes into the radical dt. Again, all of this goes into y1, second trace 7, -1 to 0, it'll shade it, etc. All right. Do just one more just to make sure that you're good here. I won't work it through all the way. Let me just make some room here. Get rid of all this stuff. It's getting a little crowded in here. In fact, let me just get rid of all this. All right, so let's say you've got a curve that looks something like that, and we're going around now the curve up here. Let's go around y equals 15 or something like that. Let's make it ridiculous. All right, so again, it's the radius that you have to be concerned with. So we'll do it here in blue. This is the integral from -1 to 0. I've got 2 pi. Now my r goes from the axis of revolution down to the curve. And again, going all the way back to chapter 6, it's not being measured from the x-axis, so you must use subtraction. It is y1 minus y2 gives you that orange section. y1 is 15. y2 is just your y value. So this is going to be 4t cubed plus 3. All of this is my r. It's y1 minus y2, and then, of course, this section in here just gets repeated inside that radical right there. That is dt. All of this then goes into y1. Let the calculator do the work for you. All right, guys, I believe I have covered everything I need to cover out of 9.3. Thanks for hanging in there. Please let me know if you have questions, and I will talk with you soon. Thanks much.